Okay, before I forget, I want to invite everyone here, everyone at the show is invited for a free dinner at, I won't say the name correctly, I cannot pronounce the Portuguese correct, but Barbacoa, at just after the show, 7:30. We've reserved a table for up to 20 people, and if you want to join us for dinner, free drinks, free food, just come by our booth and sign up, and so we know how many people are coming. But everyone's invited, and hope to see you there. Just after the show, right after, we'll meet at the restaurant. The show ends at 7, so just right after 7, we'll start eating around 7:30. So, okay, I have an uncle. My uncle has never flown his entire life in an airplane. And the reason he says he's never flown his entire life in an airplane is because he says airplanes are dangerous. The same uncle drives his truck almost every day. Okay, so let's look at the real numbers. I think you already know what the answer is going to be. But what's more dangerous, airplanes or passenger vehicles? So in 2013, there were 224 deaths as a result of airplane accidents. The same year, there were more than 1.25 million deaths as a result of vehicular accidents. So what this picture tells us, something we already know, is that vehicles, the products that you and I help to produce, our companies are involved in the production of vehicles, they're dangerous. The product that we make is dangerous. And in fact, you can argue that the automobile, by number of deaths per year, is one of the most dangerous products produced on the face of the earth. The good news is that the number of deaths is going down and down over time when you reference it in terms of number of miles driven. So vehicles are getting safer. That's good news. The reason why they're getting safer is in large part because of the vehicle itself, the vehicle systems. The vehicle's materials are getting better. Electrical systems can detect when there's going to be a collision with advanced driver assistance systems. Braking systems are getting better, and on and on and on. And that's where you and I come into play. Without testing, without development, none of these improvements are going to make it into market. If we look at vehicular emissions, the amount of pollution emitted into the environment, into the atmosphere, we see a similar picture. Vehicle emissions is second to only electricity production in terms of the amount of greenhouse gases emitted into the atmosphere. And you can make an argument that relative to human health of humans, vehicular emissions and pollution is much more important than electricity production, mainly because most of the electricity is produced outside of city centers, whereas vehicles are driven inside of city centers. Also, the good news is emissions is coming down. We know this. Electrical vehicles are coming out. We have hybrids, start-stop systems, on and on and on, and even combustion engines, whether they're two-wheelers or vehicles or on-highway trucks. Because of our efforts, they're getting better. Pollution's going down. None of this can happen without you and I. So the main point of these first few slides is to make the point that what we do, it matters. It makes a difference. It is important. How about autonomous driving? I want to do a survey by way of show of hands. Who in this room thinks autonomous driving is going to make the world a safer place? How many hands do we get? Autonomous driving is going to make the world a safer place. Okay? How many think that autonomous driving is going to make the world less safe of a place? Okay, I got one hand, but two hands. Okay. So this quick survey already tells me what I already know. I agree that I'm in the camp. I believe that autonomous driving will make the world a safer place. And most of you in here felt the same way. By show of hands, I saw by far more hands saying autonomous driving is going to make the world a safer place. You and I are both in the auto industry. When I talk to my family and friends outside of the auto industry, outside of technology, and I say autonomous driving, a computer's going to drive your car for you, they're terrified of the idea, horrified of the idea. So really, most people, I think, outside of the industry really believe that they're just terrified of autonomous driving, for by and large. And I have in my pocket, if I can find it, I have a $100 bill. This is a United States currency, but you can exchange it to whatever local currency you want. I'm going to ask it a question, and I'm looking for a one-word answer. And whoever gets the answer correct is going to get this $100 bill. Okay? One-word answer, you got to raise your hands. What is going to be the major factor whether autonomous vehicles are going to be safe and make the world a safer place or less safe place? I need a one-word answer. What's the biggest factor?
Ethics.
Which one?
Ethics.
Ethics? That's not the answer I was looking for. Anyone else want to try? Yes, back here. Okay. What did you say? I didn't hear you. Humans. I'm looking for a little more personal answer than that. Accuracy? That's all good stuff. Which one? Okay. You want some money first. No, you give me results first, and then I give you money. Fear? Fear. No, I'm looking for a very personal answer. Liability. These are all good things. I'm not getting exactly the answer I'm looking for. Huh? Morals? No. Huh? No one else can get the answer? The closest answer I heard was humans, but I'm looking for something more personal than that. Politicians are going to save the day, yes. No, of course not. I'm not going to give you... Don't believe that. Any other tries? Feelings? No? The answer I'm looking for, I'll give the $100 to the guy back there because he was the closest. He said humans. It's us. It's you and me in the industry that are going to be doing the testing and going to be doing the development. It's you and me. It's us. Whether it's successful or unsuccessful depends on us. If we do testing poorly, the vehicles that we release into the world are not going to be safe. If we do testing correctly in development, they will be safe. It's that simple. It really depends on us. So I'll give the $100 back to the human answer. There we go. Yeah. There we go. Okay, so that $100 bill actually reminds me of a story I wanted to tell you guys too. The $100 bill, there was a what do you call it? In the U.S. there was a big, I can't remember the word I'm looking for, but there's a big problem in the U.S. Earlier this year, the United States government announced that it was going to change the face, the person on a $20 bill. So currently on the U.S. currency, $20 bill has the United States President Andrew Jackson, which is, the $20 bill is one of the most popular bills in the U.S. And the U.S. government said, we're going to change that. We're going to replace Andrew Jackson with Harriet Tubman. And Harriet Tubman was a slave abolitionist, and she helped to eradicate slavery in the U.S. And a lot of people got upset about that. They're like, what? Are you kidding me? You're going to replace a U.S. president with someone that was never a president? We've got, on the $1 bill, we got George Washington. On the $5 bill, we have Abraham Lincoln. And on the $100 bill, we have Benjamin Franklin. Isn't it a law that you have to have a U.S. president as, on the currency? What escaped those people's minds that got so mad about this was that Benjamin Franklin was never a U.S. president. So I think a lot of those same people are probably going to vote for Donald Trump this upcoming election. So, yeah, I get the question a lot. Who are you going to vote for? I mean, I got Donald Trump on the right, Hillary Clinton on the left. And I think no matter what the result is, the United States is in trouble. That's my personal opinion. But this presentation is not about politics. It's about automotive Ethernet and testing. So let's talk about that. Before we talk about that, let's talk about the state of Ethernet in cars. The state of automotive Ethernet. That means bringing the Ethernet technology that's used in the standard computer world and IT world and bringing that into the vehicle. First thing is that it's already too big to fail. We've got so many OEMs, big ones like General Motors, like VW, like BMW, like Renault, like the list goes on and on. These big companies, these big multinational OEMs have already production plans for automotive Ethernet in most of their vehicles in the future. Automotive Ethernet is going to be the technology that's going to support, that's going to be the base technology that's going to support a lot of the things that we want to do in the industry for improving safety, for improving emissions in the vehicle. So that's where the state is right now, Ethernet. It's going to be the big technology in cars in the future that's going to help us achieve the results that we want. Unfortunately, most of us are familiar with the world of CAN, controller area network, as a vehicular networking technology. And in the CAN world, things are relatively simple. You have a CAN physical layer that's the electrons actually happening on the network. CAN controller does the messaging, sending and receiving frames, detecting errors. We have ISO 15765-2. This gives us the ability to transmit more than 8 bytes on a CAN network, because the maximum frame length on a CAN network is 8 bytes. And then we have a small number of high-level application layer protocols. The most popular one is called UDS, or ISO 14229. That gives us the ability to send fault codes, read fault codes, download new software into the ECU, reconfigure the ECU for different applications in different vehicles. And then GM has its own flavor, GM LAN. But the point here is that in this world we have relatively few, I can count them on my hand, worldwide different protocols that are used on top of CAN. There's not a lot of different types of protocols used in the CAN world. And if you want to contrast that with Ethernet, it's a big difference. It's a huge difference. So when we talk about Ethernet, we talk about a physical layer as well. We have currently in production we have broad R reach, which is 100 megabits per second. And then on top of that, we have an Ethernet MAC, a media access controller. And the media access controller is not that different than a CAN controller. It's basically, you have a header, you have data, you have a footer with a typical redundancy check, you have interframe spacing. So the frame itself of Ethernet is relatively similar to CAN. It's not any kind of rocket science. But where things start getting crazy is above that. So we have two main pillars of protocols here. One is our TCP/IP suite, which includes address resolution protocol, ARP, IP, Internet Protocol, ICMP, Internet Control Message Protocol, TCP, UDP gives us the ability to transmit a lot of data on the network. And then we have tons and tons of application layer protocols like HTTP, Hypertext Transfer Protocol, FTP, File Transfer Protocol, and many hundreds, if not thousands, of other ones. So there's many, many protocols that are used in automotive Ethernet. All of these are used in automotive Ethernet, and there's many hundreds more. All of these protocols, none of them are real time. None of them serve the purpose for real time, safety critical communication. For those purposes, real time safety critical applications have got this pillar of communications here. It's the AVB TSN suite of protocols, and that stands for Audio Video Bridging, and TSN is a newer name for it. It's called Time Sensitive Networking. And Time Sensitive Networking is specifically designed for real-time safety critical applications, but unfortunately it consists of a whole lot of protocols that are all mixed together. IEEE 1722 is AVTP, that's the transport layer for getting video and audio data across the network in real time. We have PTP, Precision Time Protocol. That gives us the ability to share a common clock across the network so that all the ECUs are very accurately aligned in real time. SRP, Stream Reservation Protocol, what that gives you is the ability for an ECU to say, hey, I need so much bandwidth on the network, and I need this for a certain, this amount of time. So it can reserve an amount of bandwidth on the network so that it can be guaranteed that its data can get out in the time that it needs to. And then we have FQTSS, which is a shaping algorithm that gives you the ability to have a nice even flow of data across the network and not have big chunks of choppy data, which all these things are very important for real-time safety critical applications. So if you haven't got the picture, the whole point of this slide is just to say that the world that we know and can is going to get more complicated when we see Ethernet come into play. And likewise, testing of those networks are going to be a lot more complicated as well. I showed this slide last year, but it's no less relevant this year. So hopefully this is new to some of you. What I did last year was I took a 2004 vehicle and I measured how much data is on the network, how much completely on the network, how much information is going across the entire vehicle. And a 2004 model year car was about 5,440 bytes per second. In 2013, I took the same model, the same type of vehicle from the same manufacturer. It was also CAN. It had many CAN networks in this vehicle. And we saw a big increase in data. 16,474 bytes per second. That's a big increase. I did the same thing for a 2016 model year vehicle with Automotive Ethernet. So this is what it looks like in the current world with Automotive Ethernet, the amount of data on the network. So this is another graphical representation of how our world in testing is going to get more complicated and more difficult moving forward into the future. Okay, so now we finally come to standardized testing of Ethernet. There are two main organizations involved in Ethernet standardization as far as testing goes. One is the AVNU Alliance. AVNU is taking care of the protocols related to time-sensitive networking and ABB. It's been an organization that did ABB long before ABB was used in automobiles. ABB was used for audio systems and professional concerts and things like that, and over Ethernet. And this group has been around for a long time. And now, Intrepid, we're part of this group, and we're developing standards to be able to test those real-time safety critical applications. Another group is Open Alliance, which is an industry conglomerate group with many suppliers. Most suppliers and OBMs are part of this group. And this group is taking care of, at least one part of this group is taking care of automated testing for the TCP/IP suite of protocols, including address resolution protocol, IP, and on and on and on. So why do we want to do standardized testing? If we look at the CAN world, for the most part, I would say most OEMs have their own proprietary specifications for CAN testing, for diagnostics testing. If we try to reproduce that in the Ethernet world, it's going to be a huge amount of work. So one thing that standardized testing gives us is it gives us the ability to pool resources into one group that then can produce a more robust standard. And another reason why you get a more robust standard through standard organizations as opposed to each OEM doing their own thing is because open specifications can be peer reviewed. And we see this in other industries. You can make a specification, other people are going to read it, and they're going to see problems with it, and the specification can get updated. So open specifications for testing gives you the ability, it promotes efficiency and promotes robustness in the sense that it can be peer reviewed. Whereas proprietary standards don't give you that as much. So those are some of the reasons. In long term even, standardized testing, if we can convince our governments that this standardized testing actually means that the vehicle's safe, can actually reduce liability. So you can say, I passed this standard test, and therefore my vehicle is safe, and therefore my liability in the marketplace, if there happens to be an accident, is less. And this would be huge for automobile OEMs if we could achieve that. And it's not like, we do this already in other parts of the industry, right? You have standardized tests in the US. You have to pass a standardized test to sell your vehicle for crash testing. Standardized test. If you pass the test, your vehicle's deemed safe, and you can sell the car. If you don't pass, you can't sell the car. Same thing for emissions. So vehicle emissions is no different than crash test worthiness. So why not take this and apply it into the electrical world of the vehicle? And I think this is something that will be necessary long term, because as we all know, you and I both know, the electrification of the vehicle is going up and up and up, and all of the functionality of the vehicle is going into the software. And so these types of testing, standard testing, and safety testing on top of the electrical systems of the vehicle is going to be more and more important as we move into the future. And just to give you an idea of how much work Open Alliance did, I'm not a small person, I'm not a huge person, I'm not small either though. And you can see I'm holding this is the specification, it's multi-thousand pages. I was going to bring it with me, but it made my luggage too heavy, so I can't actually show it to you. And so I had to leave that at home, but it's a huge thing of lots of different testing. And this is only the TCP/IP suite of protocols. That's it. Another way you can look at the complexity of Ethernet and the testing that we have to do. Intrepid Controls, we wrote a book on Automotive Ethernet, so if you're interested in Automotive Ethernet, we wrote a book on it. And we'll even give you a free book. Come by our booth and sign up, and I'll promise to send you a free book. And this explains all the protocols that exist on Automotive Ethernet. So it's more than a 1,000-page book. Okay, so of course, our main business at my company that I work for is Intrepid Control Systems. We make test tools, and this is just an example of how an automated test for a standardized test might look like. This is our vehicle spy software with a standard graphical user interface that you can customize, and you can push a button here, run your ECU through a standardized sequence of tests. This particular one tests ARP, Address Resolution Protocol, and out comes a standardized report as well. With our tool, you can customize a report, but this just gives you an idea of what the TCA, this is the Open Alliance Technical Committee 8 that creates these tests, what that looks like. In the ABB world, it's similar as well. The ABNU Alliance is generating test specifications for what needs to be tested for ABB and PTP. And likewise, Intrepid Controls, our tools are designed to be able to run those tests. So this is just an example. In the ABB and TSN world, things are real time. So it means the ability for the test tool to measure very accurate time across multiple networks is very important. So this just gives you an example of a part of PTP that's called the link delay. It measures the amount of time it takes for one message to go from one ECU to the next ECU. So all ECUs know their peer link delays and therefore can make corrections to time clock across the network. And so with Vehicle Spy, you can measure these delays to an accuracy, with our hardware as well, to an accuracy of 10 nanoseconds. So it does take very special hardware for this type of testing. And the hardware that we produce is called Rad Galaxy. Inside of it, if you're interested, if you're in the tech world or electronics world, it's a huge FPGA code that we wrote ourselves, and it has 10 nanosecond timestamp accuracy across all networks. It can do up to 6 Ethernet networks and 8 CAN networks at the same time, and includes automotive requirements around testing. So most vehicles are tested at minus 40 degrees. This hardware will work at minus 40 degrees, up to 85 degrees, and also fits the automotive specifications for voltage ranges as well. So in cold weather testing, you can do a cold crank and the voltage on the battery can go down to around 5 volts. This device will still work down at that low voltage all the way up to, the on-highway trucks, a 24 volt system. There's a test that's called a low dump, and the voltages on a low dump on a 24 volt system will go up to 40 volts. So that's sort of, we take care of both the on-highway truck construction equipment world at the high end, and 24 volt systems, as well as the 12 volt systems that are in passenger cars at the low end for cold cranking. So it's a very specialized hardware that needs to be employed, like the Rad Galaxy, for this type of standardized testing. But good news is, Intrepid Controls makes such a thing. There are some real cool things that are happening in the Ethernet world as well. Ethernet's not staying still, so if we get into standardized testing, the standardized tests are going to have to change and evolve over time for new functionality, because there is a lot of new functionality that's happening in Ethernet. One of them is called frame preemption. Frame preemption essentially gives you the ability to start transmitting a message on the network, and then if a higher priority message comes in or needs to be transmitted, you stop right in the middle of the frame. You stop transmitting the lower priority frame. Then you can transmit the entirety of the higher priority frame. And then after the higher priority frame is completely transmitted, you finish, the remainder of the lower priority message then can go out afterwards. So it's a way to preempt lower priority frames, higher priority frames go out, and it gives you a much lower latency, much higher transmission speeds across the entire network than what you can achieve without frame preemption. This is just one example of new functionality that's coming out in Ethernet, and it's specifically designed for real-time safety critical applications like ADAS systems, autonomous driving. Also, time-aware scheduler. This gives you the ability essentially to very accurately, with very little jitter, send messages in periodic form with a very high accuracy. So those are two things that are coming out. The good news is that because we have designed in our hardware FPGA, it's really just a firmware upgrade to support these new features. So in our hardware, we sort of try to future-proof it, and these advanced features, as they come out, will be supported in our tool. Okay, summary is first of all, automotive Ethernet is going to be a big part of automobiles in the future, especially when we talk about autonomous driving, especially when we talk about ADAS systems, safety critical type applications. Standardization of testing can improve efficiency. It can help us, because if each OEM had to create their own specification, it would take a lot of work for that OEM. It would be less work for the OEMs if they combine together and create a standard. Open standards also have the ability to be peer reviewed and improved that way. And long-term could even reduce liability for OEMs. And Traffic Controls wants to help you if you find yourself in the need of wireless data loggers, embedded data loggers, or vehicle network test tools. I want you to come and see me. And the last thing I want to say to summarize everything, and this is the most important thing in the presentation, you can forget everything else, and remember this one point. There are almost 4 billion people in the world living in city centers. 4 billion. About half of the Earth's population lives in city centers. And that number is going to increase as in terms of percentage over time. So in the future, there's going to be more than 50% of the Earth's population living in city centers. That number's going to go up. 4 billion people. 100% of those 4 billion people are affected by vehicle safety. 100%. 100% of those people are affected by vehicular emissions. When we work together and we produce something that's new, it's very unfortunate that when we create a new safety system and that safety system triggers and actually saves someone's life, it's unfortunate we don't get a thank you card in the mail. We don't get that as engineers. But please remember, it doesn't mean that it doesn't happen. It doesn't mean that it's not real. It doesn't mean that our work doesn't save lives. It does. It improves lives and saves lives. When you improve emissions on a vehicle, you're not affecting 100 people, you're not affecting 1,000 people, you're not affecting 1 million people even. You're affecting billions of people. So we got to do our work with pride, we got to do our work with passion, and we got to do our work with persistence. Thank you for your time.